Hi there everybody, it's Mr. Pope from Winton Grammar School for Boys, and this is the 8th mechanics session, and today we're going to be looking at centres of masses of laminas. So before we begin, this topic would be in further maths. For the new topic it would be in further mechanics 2. In the old specification it was in under M2. If you want to use physics and maths tutor, physicsandmathstutor.com to find any past papers, that kind of thing, and work through them, be my guest. It's definitely worth having a look. And you'll probably notice that I got quite a lot of my questions from there. Okay, that being said, all this stuff here, okay, is given to you in the formula book. Okay, so you don't need to memorize these at any point in time, and to be honest, that's quite good. Where these things come from, we probably have to do a little bit of calculus first, but first of all, let's describe what a lamina is. So a lamina, you can imagine, is kind of like a sheet of a material. So say, for example, I could have this square, that's supposed to be a square, and you could treat this square as having infinite thinness, if that's even a word. It's infinitely thin, and you can treat it like a sheet. So it's infinitely thin. Okay, the other thing you can think of is, what does it mean to be uniformly distributed? Or rather, its mass, its density is uniform. That just means it's made out of the same material, and it doesn't matter if I take a small section like this, or rather if I was to cut, it wouldn't matter if I was to cut a smaller square this big, or I was to cut the square here or here or here or here. These should all have the same mass. It's equally spread out, i.e. the mass, the weight, is going to be the same wherever. So that's really important. The next thing to notice is, what do I mean by a centre of mass? Okay, what does it mean, a centre of mass? And essentially what that means is if I was to imagine that this square, the centre of mass is a point where the mass of the object acts. Okay, so it's essentially a point on an object where, and for a square, by symmetry, it's going to be dead in the middle, and it's going to be a point as if where that mass of that object acts. So at the moment, this square would be hanging downwards like that. If I was to turn the square sideways, the sheet lamina, then from the side it would look like a flat object, and then the idea is that the centre of mass viewed from side on would be in the middle, and the centre of mass means that you should be able to put your finger on that spot. That's supposed to be a thumb, and it would balance. Okay, a practical application is that you should be able to balance an object upon its centre of mass like that. Okay, now there's various ways of finding the centres of masses of objects, and what it comes down to, or what I'm going to be looking at today without calculus, and next time we're going to be looking at stuff with calculus. Let me just double check. Yeah, so next time I do a mechanics stuff, we're going to be looking at the integral formulas for finding the surface area, to find the mass of any particular function. But at the moment I'm just going to be looking at some simple shapes, that is triangles, rectangles, circles and sectors of circles. For three-dimensional shapes, for three-dimensional shapes and onwards, we're going to be needing to use some kind of volume of revolution or some integral tricks there. So we're not going to be covering that today. But today we're just going to be looking at some simple laminar two-dimensional shapes. So the idea is as follows. This centre of mass, if you treat this like a coordinate system, and it doesn't matter where you treat it as, let's say that corner is my XY coordinate system. Okay, then where the centre of mass is going to be X bar, Y bar. Okay, we say the centre of mass is at a point X bar, Y bar. And it's really, really simple. X bar is just going to be the sum of all the masses times by the distance away. Let's say a mass of a point, xi of a point, and then that's divided by the sum of all the masses. Okay, so if you'd like to think about it, this top thing is mass times by the distance away. So these are actually the moments from the origin. And then on the bottom, this is just the total mass. And the reason we do that is because the moments are going to be kilograms times by distance, let's say meters. The mass on the bottom is in kilograms, so we're going to have kg times m over kg. The kg cancels, and m is in meters, and we want the SI units of x bar to be in meters. So dividing by the sum of the masses, it's like a weighted average. You know, you're saying, okay, proportional to not only how big a point is in terms of its mass, but also how far away it is, because the further away it is, the less it's going to contribute, or rather it's going to have a greater moment, you know. And then by similar logic, y bar is just going to be the sum of the masses going from I, and let's say I goes from 1 to n, I goes from 1 to n, I goes from 1 to n, and this is going to be mi, yi, and this is going to be the sum from 1 to n of not y, you silly boy, the mass. Okay, so m1, m2, m3 is just the masses in the system, and x1, x2 and so on are the x coordinates of those masses. Or rather, I should just put x1, y1, x2, y2 and so on are just the coordinates of those masses. So let's deal with this then. So suppose we've got three points. Okay, let's say I've got 3 points, and 1 point is at the origin and it weighs 1 kilograms. Another point is over here and it weighs 4 kilograms, and its coordinates are, let's say, 1, 5. And let's say I've got another point over here where this is 2 kilograms and this one's coordinates are 4, 1. And now imagine we've got, let's move this 4 kilogram out of the way. Let's imagine we've got a wireframe like this that's attaching the 3 weights. Okay, and then let's suppose that the gap in the middle is filled with a really light plastic, i.e. the plastic is not heavy at all, it has 0 mass. The question is if I was to construct a shape, or rather the mass is so small, like less than a gram, so it doesn't make a difference when compared to a kilogram, 2 kilograms, and so on. And let's say this magical plastic doesn't break under the weight of the masses. And the question is, where should I stick my finger so that, lol, so if I was to have this lamina, and where would I put my finger or some other object so it would balance properly? So the question is, where is that? Well, this is going to be quite easy, because the x bar is just going to be the sum of the masses times by the x coordinates. So it's just going to be 1 times by 0, because the x coordinate of the 1 kilogram is 0, plus the 4 kilograms times by the 1, plus the 2 kilograms times by the 4, and then this is over the sum of the masses, which is 1 plus 2 plus 4. So I'm going to have a 0 there, a 4 there, and an 8. So that's 12 over 1 plus 2 plus 4, which is actually a 7. So x bar is actually going to be 12/7. Okay, y bar we can construct in a similar way. So it's going to be the masses, so 1 times by the y coordinate, which is 0, plus the 4 kilogram mass, which now has a y coordinate of 5, plus the 2 kilogram mass, which is a y coordinate of 1, and this is over the sum of the masses, so 1 plus 2 plus 4. Well, that's a 0. 4 times 5 is 20, so that's going to be 22 over 1 plus 2 plus 4, which is 7. So y bar is 22 over 7. So this coordinate here is actually 12 over 7 and 22 over 7. Right, now, you could do this with triangles, you can do it with circles, you can do it with various other things. But, well, with point masses. But what we're going to do now, okay, is with triangles, there's a very special property, okay, and that is if you go 2/3 of the way along the median from a vertex, you'll get the center. So what do I mean by that? Right, the median means if I take the halfway point of one side, say there, that is terrible, by the way. Oh wow. Right, let's go back. Right, where is the center? Well, the median is if I take the halfway point between 2 points like that on this triangle, and then I join a vertex like that, that is called a median. Notice it's not 90 degrees. 90 degrees would be if I dropped it down there, say. That would be a perpendicular. That's not a perpendicular, this is called a median. Now, if I cut the triangle, another side of it in half, say that, and then I join the opposite vertex like so, and then I joined another vertex to the opposite half, which is over here. So this is the same as that, these two are the same as these two, and this side is the same as that one. Then this point here is also the centre of maths. And that point, which I'll call A, is actually x bar, y bar. And it's interesting to note that from here to there is exactly 2/3 of from here to here. Similarly, from here to there is 2/3, and this is 1/3. This is 2/3, and the final other side is 1/3. So, if you don't have to necessarily do all this stuff again for that. But with a triangle, it's just very simple. If I draw from a vertex to the midpoint of another line on the triangle, then I only have to go 2/3 of the way along in order to get the center. To prove that, I'm going to need to use calculus. So we're going to have to save that for the next video. And we've got some other interesting facts here as well. And these are going to be the main ones today. Okay, triangular laminas 2/3 along the median, circular arcs. Okay, what does that mean? It means if I've just got a circular arc like this, so think of it as like a bent toothpick, or not bent toothpick, like a bent paper clip, as in it's just a wire, then imagine if you were to draw a radius from these two and they meet a point here, then if you call this angle 2 alpha, then the centre of mass is a distance from that centre to there. So the centre of mass is about there, and that centre of mass is r sine alpha over alpha. Now you're probably thinking, hold on a minute, what does that even mean? You know, what does it mean to have a centre of mass that's not on the object? And well, what does that mean? It means that if I was to put, well, if you was to say have a composite shape, say for example you've got a rectangular lamina like this, and this is a solid thing, and then you have a wire acting like this, where this is all empty space, then you would have to consider a weighted average of the centre of mass of this square plus the centre of mass of this wireframe thing. So the centre of mass of the whole thing would be somewhere like that. Okay, you've got to think of it as it might contribute to a bigger object. Okay, and all it is just taking weighted averages, i.e. by following this formula here. Okay, so when you use, say, the xi, then in this example, say from here to here was 2, and then from here to here was 1, then if you let this corner be your xy axis, then clearly the centre of mass of this, if you called it a square, where it's a 2 by 2 square, then what you would do is you would say, well, let's say the I don't know, let's say the square weighs a kilogram, and let's say the bent wire also weighs a kilogram, say, then it would be the mass of the square, which is 1, times by the x distance away from wherever you put your coordinate system, so that would be 1, plus the mass of your rod, which would be 1, times by. Now let's think about what the x coordinate's going to be. It's going to be 2 plus this thing up here. So it will actually be 2 plus r, which is 1, sine of, and now what is alpha? Remember the angle is 2 alpha, so that means pi radians, a straight line, is 2 alpha. So that means alpha is pi over 2, so it's going to be sine of pi over 2 over alpha, which is pi over 2. And then this is all going to be the sum over 1 plus 1. And then that can easily be solved, because 1 times 1 is 1, plus, and then this thing will be 2 plus, sine of pi over 2 is 1, so it'll be 1 over pi over 2, so this becomes 2 over pi, and this all goes to 2. So the answer would just be 3 plus 2 over pi over 2. If you get this over a common denominator, this is going to be 3 pi plus 2 all over 2 pi. So the true centre of mass, this thing here, is going to be 3 pi plus 2 all divided by 2 pi units to the right from this. And you can actually tell from symmetry, this is going to be x bar, and you can tell from symmetry y bar is just going to be 1, because there's clearly some axis of symmetry going on there. So you can just tell the centre of mass is going to be there because there's reflectional symmetry among that axis. So just be really careful. A circular arc, this is for a wire, and the sector of a circle is if it was a solid. Okay, and again, we're going to need to do some calculus to prove the difference between these two. But for now, just use them. Okay. As they are. Now, there's a couple of tricky things with this. For example, let's say you've got a rectangle. Let's say that's a rectangle, but then there's like a rectangular piece missing. Okay, so let's say this is a solid and there's a rectangular piece missing. Okay, how would you solve this problem? And that's also really simple, because what you need to do is you treat the whole as if it's negative mass. I'll show you what I mean by that. So let's say I've got a rectangle like this, and I don't know, let's say this distance from there to there is I don't know, let's say it's 8 units, whatever it is, and from there to there, let's say that's 6. Let's say from here to here is 3, and this is a 1 by 1, and then let's say that distance from there to there is 1 as well. So there's a 1 by 1 square cut out of a 6 by 8 rectangle, and let's say, for argument's sake, the density of this shape is 1 kilogram per units squared. So the mass of the whole shape is clearly 8 times 6, which is 48, minus the 1 by 1 square, which is 47. So the total mass is just 47 kilograms. So how would I find where the centre of mass is? Well, you would do x bar would be the sum of the mass, so it would be 48 times by. Now let's consider the x coordinate. Let's consider the axis down here in the bottom left. Well, if it's 6 wide, then the centre should be 3 along, right? Because the centre of mass, you know, by symmetry, is dead in the middle of the rectangle like that. And now, because there's an empty space square there, imagine that density is being taken away. So it would be its area, which is 1, times by the coordinate of it. Well, let's think about it. Where would that be? Well, I'd have to go back 1.5, right? Because that would be half. I'd have to go back 1.5 from 6, which is 4.5, and it's a negative area, so I'd minus 1. I'd minus that, and then this would be all over the total mass, which is 47. So that is just a little calculation job. So 48 times 3 minus 4.5, and divide that by 47, and we get x bar is 279 over 94 units to the right, which is 2 and 91/94. Okay, so why does that make sense? Well, because the centre of mass would normally be in the middle, right? But because it's slightly lighter on the right hand side because of this hole, that centre of mass is actually going to be dragged to the left a little bit, isn't it? Because there's more stuff on the left hand side. So you would expect the centre of mass to shift over a little bit. And we can do a similar thing with y bar. Well, similarly, the big rectangle is going to be 48, the y position is going to be 4 ordinarily, and then minus the negative mass of, well, it would be 3.5 up in the air, and this will all be over 47. So it'll be 48 times 4 minus 3.5 all over 47. So that's going to be 4 and 1/94. And so again, we would expect the centre of mass of the big rectangle, if that little bit wasn't there, to be at 4. Because Clearly, the little rectangle is cut out just below the halfway line. We would expect the centre of mass to have shifted up a little bit. And in this case, it's shifted up by 1/94. So there you go. Because of taking a little square out in the bottom right-hand corner-ish, that shifted the centre of mass of the whole object up left a little bit to counteract that. Yeah. There's loads of things you can do with this. I'm just going to go through a few questions. Hopefully you guys get the gist of it. It's honestly not that big of a deal. I wanted to throw you guys a bone because I've been throwing some hard stuff at you lately. So let's go through this. If you want to try it for yourself, be my guest. Pause the video. So it even reminds you in the question, the centre of mass of a semicircular lamina of radius r is 4r over 3 pi. And why is that? Because it's 2r times by sine of pi over 2 all over 3 pi over 2, isn't it? So if I look up here, for a sector of a circle, when the angle is pi, that means 2 alpha is pi, that means alpha is pi over 2. So I've got sine of pi over 2 times 2r all over 3 times pi over 2. And if we think about this very carefully, this means we're going to have 2r times sine of pi over 2, which is just 1, so that's 2r times 1. And then I've got 3 pi all over 2, so then the 2 comes up the top. So I'm clearly going to have 4r over 3 pi. So what they've actually done there is they've given you the formula and they've just, I've just made it a little bit easier for yourself. Right, the template consists of a uniform plane lamina PQROS, as shown in the diagram above. The lamina is bounded by two semicircles of diameters SO and OR, and by the sides SP, PQ, and QR of the rectangle PQRS. The point O is the midpoint of SR, and PQ equals 12 and QR equals 2x. Show the centre of mass of T is that from SR. Okay, since SR is the distance we're interested in, I'm going to make SR my X, Y, my point of reference when I'm going to draw my centre of mass from. So, where are the centre of masses going to be? Well, the centre of mass for this semicircle is going to be here. Well, that's 4r over 3 pi up. And the other centre semicircle is going to be that, which is 4r over 3 pi. And notice, if the whole thing is 12, then each semicircle has a diameter of 6, so each radius is 3. Well, that means if r is 3, that cancels and that cancels, so it becomes 4 over pi, doesn't it? So the distance is 4 over pi up from the line. Oh dear. Stop it. It's 4 over pi up from the line SR, where the centre of masses are. So, yeah. And then where is the centre of mass for this the rectangle going to be? Well, that's going to be dead in the middle here, where from here to here is a distance of x, and from there to there is a distance of 6. Okay, and to be more specific, since we're in SR term here, I want a distance from here to here of 6, and from there to there of 2. So, because I'm interested in the distance of T from SR, really I don't need to know this 6. I'm more interested in these heights. So, Y bar is going to be the sum of all the masses. Well, let's think about that. The mass of a semicircle, and because it's proportional, it's a uniform plane, right? So we just times it by density, but then we divide by the density anyway. So it doesn't particularly matter. We just need the areas. The mass is going to be proportional to the area with these things if it's uniform, right? If the thing is uniform, then we can just treat the area as the mass. So think about it. I'm going to have pi times the radius squared, which is 9 over 2. So this has an area of 9 pi over 2, this has an area of 9 pi over 2, and the area of the rectangle is 12 times 2x, which is 24x. So y bar is going to be the mass of the rectangle, which is 24x, times by the distance down, which is 2. Is it? No, it's not. Where did I get that from? It's not 2. If this is 2x, it's a distance of x down, isn't it? Oh, I'm a silly boy. So actually, that should have been an x. Okay, and then I have to minus the mass, which is 9 pi over 2, times by the distance away, which is 4 over pi. And then for the other semicircle, I want 9 pi over 2 times by 4 over pi. And then I want to divide by the total masses. Well, it's just going to be 24x plus 9 pi over 2 plus 9 pi over 2, which is 9 pi. Okay, now, first of all to note is I could have very easily defined y to be going upwards. So I want the absolute value of this thing. I don't care, whether it's, I want to make it positive because I want a distance. So let's tidy this up. The first term is going to be 24x squared minus, and now look, the 4 and the 2 cancel, so that's a 2, pi and pi go. So I've got minus 9 times 2, which is 18, and the similar thing's going to happen over here, so I've got minus 9 times 2. So I've actually got 24x squared minus 36, the absolute distance of it, the mod of it, all over 24x plus 9 pi. Okay, next of all, I'm going to try and factorise top and bottom. So what does 24 and 36 have in common? They've got a maximum of 12 in common, so this is 12 mod 2x squared minus 3, all over. And what does 24 and 9 in common? 24 and 9 in common, they have 3, so this is going to be 8x plus 3 pi. The 12 and 3 cancel down, so the 3 can go, and 12 divided by 3 is now 4. So are we looking for 4 lots of the mod of 2x squared minus 3 all over 8x plus 3 pi? Yes, we are. Okay, not a problem. Next up, the template T is freely suspended from the point P and hangs in equilibrium. Right, so bit of a mind doozy here, but if it's hanging from P, that means the centre of the mass is going to be hanging directly below it. So that way, that angle there is facing downwards, and the horizontal is going to be perpendicular to that. Maybe I didn't talk about this in good enough detail, but now this is 90 degrees. And it's saying, given that x is 2 and that theta is the angle between PQ and the horizontal, so this angle here is theta, and if you think about it, this angle here is pi over 2 minus theta, because that adds up to a 90 because it's perpendicular to going down. And if I create a right angled triangle here, then this angle must be theta. Okay. And by the way, we're now talking about this thing, right? The new centre of mass of the object. So this is y bar. So really, I shouldn't have done that. I should have done, because the blue is the centre of mass of the rectangle on y bar. Okay, so all of this is theta. Okay, given that x is 2 and that theta is the angle that PQ makes with the horizontal, show that tan theta equals to that. Right, okay, so do you agree that vertically this distance here, if from here to here is y bar, then from here to here is 2x minus y bar. And from here to here, by symmetry, because these two semicircles are equidistant from the origin, this shape has vertical symmetry about there, so the centre of mass of the original object is going to be 6 away from there. So really what we've got is a right angled triangle where this is theta This is 2x minus y bar, and this is 6. So clearly, tan of theta is going to be the opposite, which is 6 over 2x minus y bar. And I now know what y bar is. It's over here. Now, what is y bar when x equals to 2? That is going to be 4 lots of 2 lots of 2 squared is 8, minus 3 is 5, so 4 times 5, that's 20 on the top, over 8 times 2 is 16, plus 3 pi. So that means tan of theta is 6 over 2x, well x is 2, so 2 times 2 is 4, minus y bar, which is 20 over 16 plus 3 pi. Now, all I have to do now is make this 4 a 4 times by 16 plus 3 pi over 16 plus 3 pi, so it has a common denominator with minus 20 over 16 plus 3 pi, and this is all over 6. And now if I times top and bottom by 16 plus 3 pi, I'm going to have 6 lots of 16 plus 3 pi on the top. I'm going to have 4 lots of 16 plus 3 pi on the bottom, minus 20. There's not a lot I can do here. Although, if I take 6 lots of 16 plus 3 pi on the top, and if I think about the bottom, 4 16s are 64, and if I minus 20, that becomes 44, and 4 times 3 is plus 12 pi. And then I look at the bottom, and 44 and 12 pi have a common factor of 4. So this is going to be 6 16 plus 3 pi all over 4 lots of 11 plus 3 pi. Is that right? Yeah. And then the 6 and 4 will cancel down somewhat to give a 3 and a 2. So now I can do 3 16s is 48, plus 3 lots of 3 is 9 pi, all over 2 times 11 is 22, plus 2 times 3 is 6 pi. So I'm looking for 48 plus 9 pi over 22 plus 6 pi, and we're done. It's very important to note that if you hang an object by a particular point, then what will happen is as that object sags, wherever you hang it from, so say in the example, I had this circular sector arc thing there, and I had the centre of mass was here, remember? And this distance, whatever it was r sine of alpha over alpha, was it? I can't remember. Yeah. Okay, that means if I was to hang it, say from this point, then that means it would hang where that's pointing downwards. So suppose I've got that shape, and now I take this shape, I'm going to copy it, and I was to hang it from there, it would now go like this. It would hang like that, i.e. if I drew a line straight down like so, then that if I was to hang it from that point, the centre of mass would be somewhere on that line going down. If I was to hang it from another point, say over here, I'd take this object over here, say, then if I was to hang it from that purple thing, it would find an equilibrium position like this, where if I was to draw a straight line down from where I was hanging it from, the centre of mass would be directly below it. Okay, it's the same thing here. If I took this massive shape and I hung it from P, then a line going straight down, like so, somewhere it would cross the centre of mass, which I found already. Okay. Right. Next question. If you want to pause it, have a go. And yeah. Right. Okay. So the figure above shows 4 uniform rods joined to form a rigid rectangular framework ABCD, where AB equals CD, okay, and BC equals AD, and each rod has a mass of M. Particles of mass 6M and 2M are attached to the frameworks at C and D respectively. Find the distance of the centre of mass of the loaded framework from AB and AD. Okay, so because both of them share A in common, I'm probably going to let my coordinate axes be this. So this is going to be my Y, and this is going to be my X. So if I want to know the distance from AB, I think that's looking for X bar. So because I'm going to take the uniform rods as just being light, even though it doesn't say in the question, then the horizontal distance of each of these away, I'm going to have the mass 2m times by a distance of 3a plus 6m times by 3a all over a total of 2m plus 6m, which is 8m. So not surprisingly, the 8m's cancel. What have we got? So yeah, so this is just going to be 3a, isn't it? So we're expecting the centre of mass to be somewhere on this line. Oh, each rod has a mass of m. Lol. Okay, so no, ignore that. So that means we've got a centre of mass here, we've got a centre of mass here, and here in the middle, if they're uniform. So really, I had 6m times by 3a, I had 2m times by 3a, and then I had each rod has a mass of m. Well, there's going to be m times by 3a over 2. There's going to be another m times by 3a over 2. There's going to be an m times by 0, because this one here is 0 away in the x direction. And I'm going to have another mass in the middle there, m times by 3a. And this is all going to be over the total mass, which is 6m plus 2m plus 4m's. So I can actually divide by m everywhere. So I'm going to have on the bottom over 12, 6 times 3a is 18a, 2 times 3a is plus another 6a, and then I've got a 3a over 2, I've got another 3 over 2, so that's just going to become a 3a. I've got a nothing here, and then I've got another 3a. So actually I've got 6 plus 3 plus 3, so that's 12 plus 18, I believe that's 30a over 12. Divide by 6 top and bottom to have 5a over 2. So 5a over 2 is just over 3a, so it's going to be somewhere on this line here where this distance is 5a over 2. And then distance from AD, so this is for AB, distance for AD is going to be now the y component, so it's going to be the sum of all the masses, so it's going to be 6m times by how far away it is in the y direction, so that is going to be 2a, plus the other mass, which is 2m times by 0, plus one of the rods m times by 0, plus one of the rods times by 2a, so that's the bottom one and the top one, and then I've got another m times by a, and I've got another m a, and this is all going to be over 12m again. So this can go, I can divide by m everywhere. So I've actually got 6 times 2, I've got 12a there, I've got a 2a here, and I've got another 2a there, and this is all over 12. So that's going to be 14, that's going to be 16a over 12. Divide by 4 top and bottom to get 4a over 3. So that's 4/3 of a. So it's going to be 1 1/3 up, so it's going to be about there somewhere. This loaded framework is freely suspended from B and hangs in equilibrium. Find the angle with which BC makes with the vertical. Okay, so if it hangs in equilibrium, there's going to be a line going through the centre of mass like that. and the vertical is going to be that orange line, and find the angle for which BC makes with the vertical. I want that angle theta. So so I've got tan of theta is going to be the opposite. Well, if it was 4/3 of A up, then that means that's 2/3 of A, all divided by x going along, which is 5A over 2. The A's cancel. I've got 2/3 divided by 5/2, which is 2/3 times by 2/5. So that's going to be 4/15. So that means theta is going to be the inverse tangent of 4/15. And I'm using my calculator for that one. I'm not doing that in my head. So inverse tan of 4/15 is, I want it in degrees. So set up degrees, yes, 14.93 degrees to 2 decimal places. Okay, and last one, you want to have a try at this. Pause the video. Okay, the diagram shows a metal plate is made by removing a circle of centre O and a radius 3 centimetres from a uniform rectangular lamina ABCD, where AB is 20 and BC is 10. The point O is 5 centimetres from both AB and CD, and is 6 centimetres from AD. Calculate to 3 significant figures the distance of the centre of the mass of the plate from AD. Okay. So it's pretty obvious, because this and this is 5 and the circle is radially symmetric, the centre of mass of this lamina is somewhere on this line, and I want the distance of the centre of mass from AD. So really, if I let I know what, I'll let A, because I'm looking at the next part and it's hanging from A. So if I'm letting downwards be my Y and going along is my X, then if I think about it, then my X bar is going to be the sum of the masses. Well, it doesn't particularly matter as long as it's uniform, so it would be the area, so 20 times 10, which is 200, times by the distance away. So this rectangular thing will be dead in the middle, which is 10, but now the circle is going to have a negative mass, so minus, and then its mass will be its area, so it'll be 9 pi, which is pi r squared, times by the distance away in the x direction. Well, it tells you it's 6 from the centre to that edge, and this will all be divided by the total mass, which is 200 plus 9 pi. So all I have to do is bang that in the calculator. So I've got 200 times 10, which is 2000, minus 9 times 6, which is 54 shift pi, and this is over 200 plus 9 shift pi. So to 3 significant figures. That's interesting. That's really interesting, because it's saying X bar is 8.01 to 3 significant figures. But that doesn't make sense. That means the centre of mass is probably over here somewhere, and I'd expect it to be more to the right. I've definitely done this right. 20 times 10 is 200. Yeah, the centre of mass of the circle is dead in the middle. It's pi times r squared. It's 6 from that edge. Yeah, that's weird. That's really bizarre. Oh, I've been silly. The total mass of the shape isn't 200 plus 9 pi, it's 200 minus 9 pi. It's got a negative mass. Lol. So that works out to be 10.66. So to 3SF, that's 10.7 centimetres. Okay, yeah, sorry, it's been absolute numpty. Anyway, the plate is freely suspended from A and hangs in equilibrium. So if I get rid of all this stuff, say A, so it's going to go somewhere there. Calculate the nearest degree, the angle between AB and the vertical, so that one and the vertical. Okay, well I know this opposite height is 10.7. No. I know that is 5 because it's on this line that's midway, and I know this is 10.7. So all I need to do for this part is the inverse tan of the opposite, which is 5 over 10.7. So that's easy enough to do. Shift inverse tan of 5 over 10.7. So that is going to be 25.0 degrees to 3SF. So to the nearest degree, it's 25. Okay, yeah. So a lot of this is just weighted sums, weighted averages, thinking about turning points, that kind of thing. Just draw a line from where the object is being dangled to the centre of mass, and as long as you don't make any silly mistakes and you've got these, cheat sheet to help you, it shouldn't be that much of a problem. Anyway, thanks a lot. Bye-bye.